So it's my pleasure to introduce again Professor James Davenport, who is going to talk to us about branch cuts and floor methods, perhaps with a different intonation.
So when I say branch, I don't mean the branch for a program. I don't mean the branch for a proof. I mean a branch as in, if you ever did it, complex analysis. When I say cuts, I don't mean cuts in proof theory. I mean cuts of branches. So we're going to need to think back to our early maths education. But first of all, Bourbaki and most of us, of course, since working, are very clear about what we mean by a function. For Bourbaki, we say the graph is a functional graph if the most parent every value. And then for Bourbaki, a function is a triple of a functional graph and the domain and the codomain. That's Bourbaki's definition of a function, which is wonderful, provided you actually have a functional graph, i.e. to each object there corresponds to each element of the image, there is at most one object. I sort of subscript by Bourbaki for such a total single-valued object. I'll use PA Parsevalue if I need it. And for the graph, I'm going to think of a set of x, fx, and the transpose of the graph similarly. There's a convention which is normally not written down, but it's worth stating here in most mathematics. If I write down an ambiguous object, like the square root of 2, do I mean 1.414 or minus 1.414? If I write it down several times, I always mean the same one. That's a really pretty common convention. Quite what's meant by in the same formula or occurrence or context is often not quite so clear. So, for example, root x times 1 over root x should be 1, because we can't really have one with the x as being root x as being positive, one being negative in the same form. It doesn't make sense. And lots of formulae don't make sense unless you believe that. So there's a standard formula for the roots of a cubic, but that's only true if you assume that those two square roots are the same square root, and if we assume those two cube roots are the same cube root. Even then you might think you have 6 values, but you don't. You actually have 3, because if you change the sign of the square root, these two components flip occurrences, and they're actually still the same value. So there are actually 3 values here, provided you follow this convention. I say that simply because this convention is not normally written down, and it's, as one gets more formal, conventions that are not written down get more painful.
James, may I ask?
Sure.
Will you take questions as you go?
Yes.
Then I will ask a question.
Yeah.
So does that correspond to our discussion at breakfast about essentially we're working in an extension of the semantics of these expressions in which there will be a unique denotation for that symbol assigned to all the possible occurrences within a symbolic expression?
Well, within a single subgroup, I mean, it might be a single expression, it might be a wider context.
Okay.
The context within which
yes.
it has fixed the denotation is itself not fixed.
Good.
But yes.
I mean, horrific, potentially, but
yes.
Good to be clear.
Yes.
Okay.
So, what I sometimes say is where so-and-so is the same square root of. Yes. Which you might sometimes do when you were talking, but you never write it down.
Mm-hmm.
So here are some statements about functions. The square root of z minus 1 times square root of z plus 1 is equal, possibly, to the square root of z squared minus 1. Or the square root of 1 minus z times square root of 1 plus z is possibly equal to square root of 1 minus z squared. Log z1 plus log z2 is possibly log z1 z2. Arctan x plus arctan y is possibly the arctan of x plus y over 1 minus xy. And with the standard interpretations, which I'll come to in more detail later on what I mean by that, but with what you might call, what one should call the standard interpretations, then what happens is that the first one is valid for positive when the real part of Z is positive, or actually when the real part of Z is 0, the imaginary part is positive. The second one is actually always valid, even though it looks very like the first one. The third one is valid provided that the argument of Z1 plus OZ1 is between minus pi and pi, because in the standard interpretation, the argument of a log is always between minus pi and pi. So if that, if the argument, if that sum is not in that range, it can't possibly be equal to a logarithm, a single logarithm. And the argument, question 4 is, of course, is the same, but purely about real numbers now. That's why I'm using x and y rather than z. Even for real x and y, it's only valid when x, y is less than 1. And if you've not come across this sort of thing recently and so on, you might be quite surprised by some of these and say, well, how do I know that? Why are these true or not true? And since this is a sort of formal maths course, how would I prove or disprove these? Number 4 is really quite worrying, because arctan's a nice function. It's got no branch cuts, so we can draw a nice little picture of arctan, and so on. That was question 4. And on the real lines, one way of thinking about why it can't be true is this. On R, the real part of it, an arctan lies between minus pi by 2 and pi by 2. There's an angle. And so the left-hand side of this can be, because x and y are independent, the left-hand side can be anywhere between minus pi and pi. So again, the two can't be equal. There must be a snag somewhere. One way of seeing that snag is to say that arctan has a branch cut at infinity. As you tend to plus infinity, your value tends to pi by 2. As you tend to minus infinity, your value tends to minus pi by 2. And then, so as xy goes through 1, you go from very large and positive, 1 minus xy goes from very large and positive to very large and negative, and essentially goes through that branch cut, even though you don't normally see it. And certainly when I started this piece of research, which is a long time ago, many people fell across this particular bug, because they weren't looking for that form of branch cut, and arctans of fractions tend to get generated by computer algebra systems. So, of course, a one-to-one function has an inverse function, and it's defined on the codomain of f, which becomes the domain of f inverse. One-to-one continuous function has a continuous inverse. Differentiable is a bit more complicated, because of course the f dash is 0, it's no longer going to be differentiable. And the same is true of analytic. So it all depends on it being one-to-one. In general, if I just take an arbitrary function or continuous function, differential function, its inverse is going to be multi-valued, got a function like that, and any of those could be its inverse, and so on. One way of seeing the lack of one-to-oneness is via winding numbers, but I'm not really going to go into winding numbers in this talk. Karateadori, Greg Analysis textbook, spoke only about multi-value functions. So multi-value functions, traditionally people want to distinguish them, they write capital initials for the multi-valued version. So sine inverse of 0 is 0, but the multi-valued version is 0 plus any multiple of pi. Cos inverse is 0, cos inverse of 1 is 0, and the multi-valued one is actually 0 plus any multiple of 2 pi I. So 2 pi rather. And in general, what actually happens is a bit more complicated, so if I take sine inverse of a half, that's what I get as the multi-valued version. Now what happens then gets embarrassing, because twice sine inverse of 0 is 0 plus 2k pi. If I take two different elements of sine inverse of naught, that's actually naught plus k pi. Now, if you take the implicit convention I mentioned earlier, but we always mean the same thing each time, then sine inverse naught plus sine inverse naught actually is twice sine inverse naught. If you don't have that convention, you get different results when you add and when you multiply by 2, which is sort of embarrassing, which is one reason why people have that convention. But as I say, it's generally implicit. And breaching it gets awkward. Sine inverse of naught minus sine inverse of naught, then again becomes naught plus k. Yes?
Well, that convention breaks because now the meaning of plus and minus has changed.
In the sense of one set out.
Yeah.
Exactly, yes.
Yes. So we're no longer dealing with simple expressions.
Yes, I talked about the meaning of symbols. I should have said the meaning of roots of symbols of expressions rather than symbols of functions. But yes, you say yes. It's a convention. There's reasons why people don't write it down. Yeah. We have more trouble still if I take sine inverse a half plus sine inverse a half.
Oh.
I get that, and then if I halve that, I should get things whose sine is a half, but I don't necessarily, because of the time I've taken two different ones. So, yes, sorry. So what possible solutions do we have? Well, one is we can deal with multi-value functions. It's difficult and complicated, but in one sense, intellectually honest. We're admitting that it's multi-valued. We're going to live with all the pain of that. And one way of doing that and doing analysis is to use the Riemann surface formalism, which says it maps onto Riemann surface, which is a multi-sheeted covering of the plane, and that multi-sheetedness is my multiple values. And that's, as it were, if one wants to think of it all as multi-valued meets analysis, is how we're going to do it. And that it won't stop us from any of the pain. It will let us at least talk about analysis and local and continuous branches and so on. We can choose a suitable domain on which f is single valued. That's what an awful lot of texts, particularly in sort of the more rigorous kinds of applied mathematics, will say choose a suitable open domain. On that domain, we can talk about everything. I was doing some research in this area some years ago at the joint INRIA Microsoft Centre in Paris when we were being inspected by the Microsoft head of research. He said, why should Microsoft be including branch cuts? We're a software house. I said, yes, you're a software house, and you have to implement software. And unfortunately, Intel forgot to implement the choose a suitable open domain instruction. So you have the problem. Hardware doesn't solve it. Now, the trouble is that this F inverse on my domain might not be the same as your F inverse on your domain. Indeed, even if our domains intersect, we might have different ones. And indeed, if our domains intersect more than once, because we've chosen different, but two different bananas around the origin, we might actually agree somewhere and disagree elsewhere or something else. In particular, and this is the one where it gets really painful, my choice of my open domain might not be the same choice as the guy who writes my inverse my log function, or the guy whose book of log tables I use. They might have chosen a different domain. And that, it's really this one that, as a software engineer, worries me. Or we just say, well, use standard definition. I will say I'm going to define that. I'm going to define the principal domain D, and then if I leave that domain, then I'm going to get discontinuity in my inverse. And that discontinuity is normally called a branch cut, and that's what we mean by it, as I suddenly jump from one branch to another in order to, as it were, what we're doing here is we're sacrificing continuity in order to maintain one-to-one well-definedness. And that's what we're doing. We cannot have both continuity and unique definitions of some of these functions. And a branch cutter when you sacrifice continuity. Multivariateness when you sacrifice having one value. Trouble is, the nice thing about standards is there's so many to choose from, as is said in all sorts of contexts. We're going to follow Abramowitz and Stegan, provided your printing number is greater or equal to 9. Because they changed some of the branch cuts between printings 8 and 9 and didn't tell anyone. That's a lovely piece of reverse bibliographic engineering. And in fact, the other thing is, Abramowitz and Stegan don't actually tell you what the behaviour is on the branch cut. And Kahan has written some useful text about that, which provides a set of decent definitions of what happens on the branch cut itself. Basically, you have 3 choices. You either agree with your left-hand neighbour, or agree with your right-hand neighbour, or you agree with neither. Agreeing with neither seems silly, and Kahan has a good definition of which neighbour you should agree with. This is where textbooks get interesting from the point of view of formalism. So I took Carton's text just to A, it was what I learned from, and B, it's about as formal as one can get while still being informed and understandable to undergraduates, to sort of stand typical undergraduates as opposed to lean undergraduates. You say y goes to equal to y, induces an isomorphism of the quotient r over 2 pi z, and then you get the argument is defined up to a multiple of 2 pi because he's working in r over 2 pi z, and so on. So he's got a good algebraic structure here. He defined the logarithm of t to be logarithm of its absolute value plus I times the argument, and so on. So, from the point of view of Bourbacky's definition of a function, then our graph is defined by equation 5, our image is the complexes, and our codomain is the complexes over 2 pi I z. And if you're happy with that's the codomain, it's now single valued in that codomain. And then you have the log product is the sum of the logs modulo 2 pi I, because that's where we're living. And then he's on it, and then again he says here, we have not defined as a function, meaning a function into the complexes, in the proper sense of the word. And then he says it has a branch in any simply connected open set which does not contain 0. So a given branch is a domain, some kind of image set, and then you take a point of a domain, you take a value of log there, and then you continue it. Analytic continuation, basically. And so he can produce a branch of log, as he says, across any point. So he has a completely solid definition up to and including equation 6. And then sort of thinks, well, but actually, you actually want to function into the complexes, not into complexes over 2 pi z, over 2 pi I z, and so on. And I'll say that's one of the more rigorous definitions, treatments I know from my my undergraduate days.
Sorry, Greg.
Yes.
I have a question which maybe is not. The question is, what is the meaning of equality?
What's the meaning of?
I mean, an equality. Yeah, like this one. Yes.
So here, that is equality in C/2 pi I z. Is what he's saying here, I think.
Yeah. But so what you're trying, I mean, it's a question about the general philosophy of what you're doing. So are you trying to find ways to to represent the two sides in some kind of equal way, in the usual mathematical sense? Or do you want to give a more algorithmic meaning to equality, like, like for instance, there is this idea in homotopy type theory, for instance, that equality could be more, it's not something trivial. There could be
But at the moment,
solutions for the equations. Sorry, I should have asked the question at the very end, but...
So here what I'm asking is, are these equal in the sense of abstract mathematics with a I'm not asking whether to, I'm going, a later question is how do you prove that statement, but at the moment I'm just asking if I put those expressions into a pocket calculator, or if I work them out by hand for given values of Z or Z, whatever, do I get the same number?
The meaning I have is, because that's the direction you seem to take, is, is there a way to say that there is a proof of equality, and the proof of equality includes the algorithmic, or the precise interpretation of the different symbols, so that they are equal, but according to that specific. Because that's a way to understand also, you mentioned Riemann, yes, so you choose a specific. So, the fact that they're equal comes with a proof, and the proof may take decisions about the convention, for instance, for the square root. This was your first example. Is it something like this you have in mind? Or?
But that would be one answer to these questions. What I'm trying to say is that we write down, or at least the undergraduate doing complex analysis writes down these things without thinking what he means by equality.
Yes.
Yeah, and
sorry, I'm sorry for interrupting.
No, it's a good question. So in the presence of these sorts of ambiguities,
yes, exactly.
What might we mean by equality?
Yes, because in homotopy type theory, there are also the identity, for instance, could decide that true equals false and false equals true in order to identify booleans to booleans. So identity comes with, it's not unique. So let's say the space of homotopy identities, like identity, is not singleton. It could come with different proofs and different interpretations. And since you're speaking about this, I never thought about that, but it seems okay. But sorry, I'm really...
No, it's a great question. So what do we mean by equality?
Yes.
What I mean at the moment is intentional equality of functions in the sense that I put the same value in, I get the same function out.
Yes.
So that's what I'm meaning at the moment.
At the moment, okay.
Yes. Then I had that in, yes, sorry.
Like the way you define intentional feels accidental to me, so it's like it for all inputs.
So yes, you're quite right. I meant extensional. You're quite right. Yes, thank you. Yep. Yes, it's in terms of what inputs, outputs. Sorry, I've got input there. Yes. Sorry, what was that? Yeah. So yes, we could do multi-valued ones, and then we would have our extensional equality will be of sets, and we talk about sets, and as I saw on the previous slide, this can be complicated because if you're not careful, you get, these curiosities with the set, depending exactly how you construct the sets, whether you get the same thing or not, but at least we have a definition that says, if I put a 0 into sine inverse, I will get something that's a multiple of pi. So yes, we're looking at this as use a standard definition, which, as I said, the point about the standard definitions and the branch cut is we're sacrificing continuity in order to preserve uniqueness of definition. So I've done this. So, and Cartan originally has, at equation 6, he has equality, exact equality in C over 2 pi I z. So if we look at the elementary functions, exponential is a many-to-one function. So its inverse, log, would be 1 to many, so we need to do something about it. And these days, the traditional interpretation is you choose your branch cut along the negative real axis. So e to the 1 is e. That's e plus I pi. And that's e minus I pi there. And I made my 2 pi I jump by going through the negative real axis. I say these days, in fact, I was taught the opposite. I was taught the branch cut was on the positive real axis, and it went from 0 to 2 pi I. But that's not common these days. Tan and arctan. For tan, the principal domain is typically between minus pi by 2 and pi by 2. And get branch cut for arctan, which is like that. Cot and a cot. This is the one with the parameters taken change between printing 8 and printing 9. And I said today we take the principal domain to be 0 to pi by 2. Sorry, is that right? I think it is, yes. We get a branch cut along the complement, so a branch cut for our cot. And maybe a typo on that slide. It's suddenly maybe 0 to pi. I'm sorry, I'm confused. So our branch cut for our cot is there. And yes, I think I'm writing 0 to pi. And the same is true of cos and inverse cos, and so on. And I have to emphasize, I said with inverse cotangent, the bounds and stake can change their minds. These are conventions. One picks a set of conventions. Some conventions are more consistent than others. Almost none are completely and utterly consistent. Indeed, you can prove that there are some theorems say you cannot make consistent choices of A, B, C, and D and all be correct, and so on. The only slight trouble with this slide, which is great, and if you did this sort of analysis at school or university, you did come across these probably, or some variant of them, is that, as we'll see later on, they lull us into a false sense of simplicity.
So for the cotangent should not be from 0 to pi?
Sorry?
For cotangent should not be from 0 to pi?
I think it should be, yes. I think it should be 0 to pi, not pi by 2, yes, for cotangents, I think, yes. I think there's a typo there. Thank you, yes. I think there is, yeah.
James, are you kind of trying to make a good point for category theory, that you always give a function with domain and codomain, and there, and if you want to do two different things, then if the domains and codomains are not the same, then you don't do it. You don't put an equality sign. Ever?
I wasn't going to make that point, but you're certainly quite right in the sense that, I mean, as Carton was saying, if I make my codomain C over 2 pi IZ, I'm locally happy, but of course I can't plug that into anything else. So you could argue, I've not thought about this, thank you, you could argue that I can define log precisely with a codomain of C over 2 pi IZ, and it's only when some idiot comes along and tries to plug that into C, assumes the codomain is C, that you get something different, yes. And certainly, as I said, well, even Bourbaki would carry, Bourbaki was carrying the domain and codomain with everything.
Yes.
At least in his formal definition. He didn't actually do it all the way through, but nevertheless, the formal definition of a function, Bourbaki is a domain and a codomain and the graph. Yes. Okay. So if you remember back earlier, I put up those two, and I said that the first one was not always true, the second one always was. So why should you believe me? And how would you set about proving or disproving one of these, bearing in mind that you aren't allowed to square both sides, because that destroys the ambiguity. I mean, if you want to have most multi-valued objects, there's no problem. If you want them as single-valued, you've got to be careful about which sign you're using. So how can I distinguish those two? Again, for the purpose of this, the branch cut of square root is inherited from log and is the negative real axis. So first of all, I'm going to regard the complex numbers as being x and y coordinates. Then the branch cuts for equation 1 are this. So z minus 1 has a branch cut along, well, a negative real axis, but of course now starting at x equals 1, subtracting 1. My branch cut for z plus 1 is there. My branch cut for z squared minus 1 is this. So z squared, the imaginary part of z squared is 2xy. Sorry. So the imaginary part of z squared minus 1 is 2xy, so that's 0. And the real part, x squared plus y, x squared plus y squared minus 1 is less than 0. And if you simplify that, you get this. So our branch cuts actually end up looking like that. And as we as human beings can see, this actually disconnects the complex plane. So we can't get from here to here without going through a branch cut, which is potentially worrying. Now all we can do is say, aha, these are actually semi-algebraic branch cuts are semi-algebraic sets that are defined by polynomial equations and inequalities. And if you have the misfortune of hearing me talk earlier this trimester, or you remember computer algebra, there's an algorithm which, given a bunch of semi-algebraic sets, we'll partition the real space according to semi-algebraic sets, so that you partition it into cells, which are connected subdomains, and so on. So I can do that, and furthermore, the linear algebraic decomposition will give you a sample point in each cell. In particular, it'll also prove the cells are non-empty. So we can do that. So if I go, initially let's go to x being greater than 0, oh, and I don't want to be on these little bits. So a good sample point would be 2, for example. And at 2, I get, well, the square root of z minus 1 is root 1, the square root of z plus 1 is root 3, and the square root of z minus 1 is root 3, and lo and behold, I feel very happy. Conversely, if we go out on this cell, well, there are actually 2 cells here. So I can take minus 1 plus I, for example, and then what I've done is I've put with each number its quadrant. This is an easy way to think about it without doing enormous amounts of floating point numbers. Then minus 2 plus I is in quadrant 2. And I, well, I is on the boundary 1 and 2, we'll call it quadrant 2. And the square root of anything in quadrant 2 is in quadrant 1. Because if I square something in quadrant 1, I get into either quadrant 1 or quadrant 2. And the square root of anything in quadrant 2 is actually in, as it were, the second octant of quadrant 1. So those 2 items on the left-hand side are both in quadrant 1. Their product will be in quadrant 1 or quadrant 2. This number on the right-hand side, the inside of the square root is in quadrant 3, and the square root of anything in quadrant 3 is in quadrant 4. So my left-hand side is in either quadrant 1 or 2, my right-hand side is in quadrant 4, so therefore they are not equal. You're quite happy, you take a decent calculator algebra system and put in the complex numbers and do all the square roots, and you get the same conclusion. It's just I thought I'd do it more graphically by quadrants. And the same is true of the point down here, minus 1 minus I. And if you're really pedantic, you ought to check each of the branch cuts as well, but we already know it's false. We know it's not true, universally true. And this is close to being an algorithm. It says, we take our elementary functions, for elementary functions, the branch cut is semi-algebraic, we ask for Gaussian algebraic decomposition to give us a bunch of cells, and we certainly check the full dimensional cells, and then if necessary we check the special cases, the branch cuts themselves, and we have an algorithm. In practice you would actually do it with floating point and suitable error bounds, because they're either going to be exactly equal or way apart because they're on different branches, so you can quantify what you mean by that. And you can check each sample point is true or false. Close to being an algorithm. I say close to because it's actually not quite so simple, because on each cell the proposed identity is either identically true or generically false. Let's see what I mean by that. So suppose I take my previous example and multiply it by z squared plus 2z plus 2. The reason I choose that is that z squared plus 2z plus 2 vanishes at this sample point and this sample point. So those sample points, instead of getting contradictions, I just get 0 equals 0. So it's all accidentally true at those particular sample points. How do we deal with that one? Yeah. So the answer is, this comes back to a paper we wrote some time ago. We regard these equations as power series, and Joris van der Hoeven has an explicit zero test for power series of elementary functions. He can tell how many terms he needs to take. So if that many terms are zero, then they are identically zero. And if there's a non-zero, they're non-zero. They're not identical. So he can test. He can actually have a formal identity test. He can compute the maximum number of terms he needs to take to verify that if the first lambda terms are zero, then it's identically zero. Essentially, you just look at the degree of the recurrence, and you can prove your recurrence. If it's got enough zeros, it can't produce a non-zero. But Joris van der Hoeven formalised it. So rather than just checking whether it's equal or not equal at my sample points, at the sample points themselves, I need to check whether the power series are sufficiently equal, where sufficiently is defined by Joris van der Hoeven's paper. In practice, you can choose a variety of algorithms, and we use the power series one as our backstop. But obviously, if you really prove they're non-zero, you don't bother with they're not equal, you don't bother with the power series. And there are some simpler tests for equality which which might say don't know. If they say they're equal, you can believe them. So that's good. And for the non-full dimensional cells, which are tedious because you can't do floating point arithmetic on them because you'll fall off the branch. You're standing on a branch, and if you do any calculation at all, your rounding errors will fall you off one side or the other. Instead of doing the calculations, we say, wait a moment, which of its neighbours does this branch cut adhere to? And you can say, so say the answer is the same as on the one we adhere to. Right. We've implemented this some time ago now in a Maple package called branch cuts. And for example, we give it a fairly complicated expression like arcsine of 2z to the root 1 minus z squared. It will tell you what the branch cuts are. It will draw you a nice picture, and you can ask Maple. So as an R package, we'll produce a left-hand diagram, just Maple shows you the imaginary part, and you can see there's some discontinuities in it, and which are above that diagram of branch cuts. Okay. Now I did say that a nice little list of branch cuts of elementary functions gave us a false sense of simplicity. One of the simplest non-elementary functions is the Lambert W function, which is the solution of W to W equals Z. It's provably not elementary or definable by integrals or anything else. It's a genuinely new function. You can't write it in terms of things you already know about. And its branches look like this. And in particular, if you notice we've lost all the nice properties we had. Oops, sorry. So in particular, the principal branch here doesn't go all the way to -30, so branch 1 abuts directly against branch -1 at places and other times the branch 0's in the way. These branches are defined, in fact, by elementary functions, but quite complicated ones, and they tend to the asymptotes here. So that's an example of a function whose branch cuts are not polynomial functions and so on. So it's not always as simple as the nice elementary function I did earlier. I just wanted to warn you about that one. So why am I standing here? What are the interactions between this and proving verification as I see it? Well, one point is I sketched out a proof via CAD, but that depended on even if you believe the CAD, it depended on a fair amount of calculus going on, or my tracking the complex numbers, and you have to ask yourselves, how do I do that? How do I make that formal? In an ideal world, that sketch I gave could perhaps be a tactic for a theorem prover. I mean, you've got all the high-level ideas there, which I think, you know, I do really think is a way forward, in the sense that before we produced these algorithms, no one really even knew how to verify or to check these equalities in any principled way at all. How dependent is it having a fully verified CAD, because no one's yet produced a fully verified implementation of CAD. The implementation's in COG, but they're not, I believe, fully verified. Now the other problem is, which is the other side of the coin, so this is a rather different problem, which is that people quite often use theorem provers to generate code. One example is the PhD thesis I examined a couple of months ago, which is generating code from Lean to solve optimization problems. Now that theorem prover, that code in Lean, has implicitly chosen a nice little domain on which its functions are one-to-one and so on. And has it actually chosen, and then spits out a bunch of, I think actually Fortran, to evaluate the thing into numerical optimization. Has it chosen the same branches as the Fortran has? The guy who implemented the Fortran definition of square root and more importantly, cot and so on. And the student admitted that that wasn't actually on his agenda, which is reasonable enough. I mean, we're writing a PhD thesis, and life of thesis students is finite, but it's an important point, you know. So if we're going to use these theorem provers in ways like that to generate code, we have to realise that the domain I've chosen might not be the domain that my end programming language has chosen. And then what do we do if the branch cuts aren't semi-algebraic, as in the case of Lambert W and so on? And there's been some very recent work on some slight extensions of CAD, which actually look like being quite useful in this context. I haven't had a chance to research them yet. I'm hoping that the student will come and visit me. So what are the interactions the way around? Is there anything here? And I did a bit of desk research. I looked at Lean, I looked at the Avigad Massot's book in particular, and I can see nothing there that helps me with this sort of question. In Isabel, so that's the Isabel group, and BibTech's done some funny abbreviation. There's some useful underpinning stuff about winding numbers and so on in the Isabel treatment of complex analysis. But I don't actually see any direct treatment of branch cuts as such in that. Larry Paulson did quite a lot of good work with this in metatasking, but all his actual branch cut work was by hand before he got to looking at metatasking. Rock, there's an interesting text on complex analysis in COG, but it's explicitly marked as non-constructive. It does, again, it says something about winding numbers, and so there's a bit of building blocks there, and what else I don't know. So I'll now stand here while you tell me that I've completely forgotten to take account of some brilliant research elsewhere that will answer all my problems. Thank you.